The classical low-rank matrix completion. And this is joint work with Daniel Pimentel-Alarcon, who is a former postdoc from Wisconsin, who's now on the faculty at Georgia State University, Greg Ongi and Laura Balzano at the University of Michigan, and my collaborator Rob Nowak at the University of Wisconsin. So the matrix completion problem is a problem that many of you are already familiar with. We are given a matrix, but we're only able to observe a subset of entries in that matrix. And what we'd like to be able to do is to infer what those missing or unobserved entries are. And of course, if we don't know anything else about the matrix, this is an impossible task. And so typically, we assume that there's some underlying structure in this matrix that allows us to infer those missing values. And in particular, that structure is typically algebraic. Often we think about low-rank structure. And I'm going to talk about different ways that we can generalize that notion in order to perform matrix completion in much broader settings. So the textbook or canonical example of matrix completion arises in recommender systems, say when we're trying to figure out how much different people might enjoy different movies. So we've got a collection of movies, say D different movies and N different customers. And for each customer, we see how much they like each of our different movies. And then what we'd like to do is we'd like to fill in all these missing entries. We'd like to be able to predict how much Richard is going to like When Harry Met Sally. So when we talk about low-rank matrix completion, yes?
What does the light blue mean? I want to know how much he likes Beauty and the Beast.
It's high. So when we look at these models in the context of low-rank matrix completion, one interpretation of what's going on is that under the hood, there are some representative users or movie watchers who each have their own taste profiles. And we think about each one of our actual customers as being a weighted sum of these representative users. So we might have a romance movie lover, a comedy lover, an action lover, and a horror lover. And we think about each customer, say Po Ling, as having a certain amount of alignment with the taste of each of these representatives. So we can think about Po Ling's preferences as being a weighted sum of the preferences of these representatives. And this model corresponds exactly to a subspace model. So if I want to predict how much Po Ling will like When Harry Met Sally, I see how much all these representatives like it, and multiply it by the weights. And so even though we've got D different movies in our database, and we can think about this taste profile as being a point in a D-dimensional space, in this example, that point actually lies in a four-dimensional subspace because it's spanned by these four different representative taste profiles. And so when we talk about low-rank matrix completion, what we're doing, in a sense, is we're saying each one of the columns in this matrix that we want to complete corresponds to a point in a D-dimensional space, and it can't be just anywhere in that D-dimensional space, but rather it lies along a lower dimensional subspace. And of course, if we knew what that subspace was, then we could very easily figure out what point on the subspace is the best fit to the subset of observations that we have about Po Ling's preferences and use that to fill in all the missing entries. But of course, we have all the missing entries, so we don't know what that subspace is, and we have to infer it from data. So the general mathematical formulation or setup is that we have n points in D dimensions. So we would think about this as like n customers watching D different movies. And we concatenate all of that into a matrix X. But we don't get to observe all of X. Instead, we only observe m entries per column. And throughout, omega is going to indicate where the entries we observe are located. P omega is the projection onto this set, and x omega is what we actually observe. It's this matrix X on that set omega. So when we talk about low-rank matrix completion, one way you could think about that is to say, well, let's search over all matrices X that fit our observed rankings or data on this set omega, and choose the one that has the minimal rank. And there's been a lot of work done on variants of this problem, convex relaxations of this optimization problem, optimization approaches, theoretical bounds on how much missing data we can tolerate as a function of the underlying rank, etc. But what I want to do today is go beyond this notion of low rank matrix completion and consider more nonlinear models. And nonlinear models are a pretty natural fit for a lot of real data sets. Even when we think about recommender systems, imagine that we have these two customers in our database and their ratings for different movies. So on the surface, you might think that when it comes to making a prediction for how much Po Ling is going to like When Harry Met Sally, Richard is just completely useless. When it comes to making the predictions. But if we look a little bit more closely, that's not quite the case. In fact, when we think about maybe the rank ordering of Richard's preferences, they're very similar to or consistent with Po Ling's ratings. So one interpretation of what might be going on here is that Richard and Po Ling actually have exactly the same taste in movies, but when Richard gives it a numerical score, he likes to give it a lot of nuance, he gives it a lot of careful thought, whereas Po Ling loves it or hates it. There's no in between. And so there's some underlying structure and similarity here. When we talk about low rank matrix completion, we say we want to predict Po Ling's ratings as a weighted linear sum of other people's ratings. But nonlinear models can capture the fact that different people might map their internal preferences to their external numerical ratings. And so if we can use nonlinear models, then we can perhaps capture some of the structure and make a better job at inferring the missing entries. So somewhat analogous to before, what we're interested in is the setting where each column in our matrix, again, corresponds to a point in a d-dimensional space. Again, it can't just be anywhere at all, but we're going to assume that it lies along some sort of nonlinear algebraic variety, some smooth surface in RD. And so we're going to need to break this assumption of there being a low rank matrix and think about ways that we can exploit this algebraic structure algorithmically and what we can say about how well we can impute missing entries. So I've been focusing on recommender systems because I can make lots of funny pictures, but these nonlinear effects show up in all kinds of matrix completion problems. So we see them in computer vision settings and genomic settings when we try to infer the topology of a network by looking at how packets traverse the network. So this is a really widespread phenomenon that a lot of times there's nonlinear structure that's non-trivial in matrix completion settings. And so because it's so prevalent, we're certainly not the first people who thought about trying to use nonlinear models. And one particular nonlinear model that's been very well studied in recent years is a union of subspaces model. So the idea here is that each column in our matrix now, instead of lying along one linear subspace, lies along one of several different linear subspaces. And so this is clearly a nonlinear model, but because there's this underlying somewhat linear structure, we can exploit a lot of what we know about regular matrix completion. And this kind of union of subspaces model is a good fit to real-world data sets, and here's one example of that. So this is a matrix where each entry measures the strength of an interaction between a drug and a protein. And pharmacists or pharmaceutical researchers might look at data like this in order to prioritize studies for developing different drugs. So they'd want to know if there's a particularly strong interaction so that they can try to develop a drug based on, or a pharmaceutical based on that interaction. But forming this matrix corresponds to running tens of thousands of physical experiments. It's expensive and it's time consuming. And so what they'd like to be able to do is to run a subset of those experiments and then infer what would have happened if they'd run some of the other experiments. So is a low rank matrix completion setup reasonable for this kind of data set? So if I look at my full data set and I look at the singular value spectrum, what I see is that this matrix is approximately rank 61. And so it's low-ish rank, and I could potentially do some low rank matrix completion. But I could also take this matrix and try to fit a union of subspaces model to the columns of the matrix. And it turns out that if I fit 4 different subspaces or clusters to this data, then the ranks of those clusters are 8, 12, 25, and 16. So what this suggests is that even though this matrix does have some low rank structure, there's some additional geometric structure underlying it that's not fully captured just by the low rank model. And potentially if we could use a union of subspaces model and really exploit that in an algorithm, we could be robust to even larger amounts of missing data. Okay, so unions of subspaces models are reasonable fits to many real-world data sets. And people have thought about how we could actually use it in the context of matrix completion. So one thing you could do is you could say, well, look, it's still low rank, at least sometimes, and so let me just do regular old low rank matrix completion and completely ignore the union of subspaces model. So if I have k subspaces, each of rank r, then worst case, the rank of my overall matrix is k times r. And so with that, if that product gets to be too large, then eventually low rank matrix completion is going to fail. Whereas if we can somehow exploit that underlying union of subspaces structure, we might not fail. And so there are a lot of algorithms that try to get at this, and most of them have a flavor something like this. They say, let's take our matrix with missing entries, in this picture they're the white parts, and let's do some sort of subspace clustering. So let's figure out which column belongs to which subspace. Which ones are in the red subspace or the green subspace or the blue subspace. And once I've done that clustering, then I can perform low rank matrix completion independently or separately on each one of those clusters or submatrices. And so we know we can do this completion step very well for each one of them. The problem is that when we've got a large amount of missing data, this initial clustering step is very fragile. It can perform badly, and even if we were to iterate somehow back and forth between clustering and completion, we can never really recover from a very bad initial clustering. And so this is just the Achilles heel of almost all of the methods focused on doing matrix completion for a union of subspaces model. So we're going to look at a different nonlinear model today that I mentioned earlier, which is an algebraic variety. And this is just a very simple polynomial generalization of the notion of a subspace or a linear variety. So a linear subspace is just the solution set of a system of linear equations. An algebraic variety is the solution set for a system of polynomial equations. And I have pictured here one example of an algebraic variety like this. So this is a Cayley cubic. It's based on cubic polynomials in a 3-dimensional space. You can see that it's definitely nonlinear. If I had a whole bunch of points on this space, the span of those points would be all of R3. It's definitely not low rank. And yet there's clearly some structure here that I might be able to exploit in a matrix completion-like setting. So we're going to focus on trying to perform matrix completion when the columns of our matrix lie along an algebraic variety like this. Now, one of the reasons why this is an exciting class of nonlinear models is because it's a superset for the union of subspaces model that we talked about earlier. And it's pretty easy to see with a simple example. So here I've got a union of subspaces where one subspace is the horizontal plane and the other subspace is a vertical line just going through the origin. And so if I wanted to look at the union of those two subspaces, I can write that as the solution set of a very simple system of quadratic equations. And in general, if I have a union of subspaces, k different subspaces that are defined by k different linear forms, then the product of those linear forms defines an algebraic variety that's equivalent to the union of all k of those subspaces. So the fact that a union of subspaces is an example of an algebraic variety is particularly exciting for this reason. So what I said earlier is that when we work with unions of subspaces, most algorithms have this kind of form where we first do some subspace clustering and then we do matrix completion on each cluster. And I said that the problem with that is that the clustering is very fragile when we have missing data. But if we've got a method that can directly do matrix completion for algebraic varieties without explicitly worrying about the union of subspaces structure, then we would be entirely bypassing this clustering step, which is the weak point in all of these union of subspaces algorithms. So by designing methods for these algebraic varieties, we're going to, as a byproduct, get methods for unions of subspaces that hopefully are going to have some advantages over previous methods. Okay, so how can we get at this? So at the heart of our method is a tensorization of the columns of our matrix X. So imagine that we've got one column in our matrix in D dimensions. I could take the Kronecker product of that column with itself, and I get a new column which is D squared by 1. Within that column there's some redundant products, so if I only keep the unique products, then I would have D plus 1 choose 2 unique products, and I'm going to call this X cron 2. So for example, if I'm in 3 dimensions, here's the Kronecker product of X with itself, and when I actually write it out a little more carefully, I can see that these 2 blue products are the same, the pink products are the same, the yellow products are the same, and so if I only keep the unique ones, I have this X cron 2 vector. Okay, so why is this relevant when we talk about algebraic varieties or unions of subspaces? Well, if we go back to this toy example that we had here with the union of subspaces, if I were to take all of the vectors in R3 that are inside this union of subspaces and compute the span of those vectors, that is R3. So there is no low rank structure in that original representation. But if instead I look at the span of all of the tensorized vectors corresponding to points on the union of subspaces, when I look at that, I can see one of the products in this tensor form is x1, x3, another product is x2, x3. And I know from up here, this system of quadratic equations that defines my union of subspaces tells me that both of those products have to equal 0 for any point on this union of subspaces. So the span of these tensorized vectors now lies in a 6-dimensional space, but it also lies within a 4-dimensional subspace within R6. Okay, so we've moved into a higher dimensional space, but now in this higher dimensional space we have some low rank structure or rank deficient. And the hope is that we'll be able to exploit that rank deficiency in order to do matrix completion. Are there any questions so far? Okay, great. Okay, so I talked about this tensorized data representation for a single column. So if my original matrix X is just the concatenation of all those columns, then my matrix cron 2 is just going to correspond to the concatenation of all my tensorized columns, and I'm going to work with this matrix. So originally what we said was that we wanted to complete a partially observed matrix X under the assumption that all of the columns lie on some nonlinear algebraic variety. And now what we're going to do is we're going to translate that goal to saying we want to perform matrix completion or impute the missing values of X under the assumption that this tensorized version of the matrix has low rank. And so somewhat analogously to what we considered before, for low rank matrix completion, we could say, let me try to find a matrix X that fits all of my observed entries and yet has the smallest rank of the tensorized matrix. So the expression that I wrote for regular low rank matrix completion at the beginning looked exactly the same, except it didn't have this sort of tensorized form in here. So we're adding in this tensorized form. So as with regular low rank matrix completion, we can't solve this exactly in a reasonable amount of time, and we have to look at various relaxations. So let me describe one approach that you might use to try to perform completion using this tensorized structure. So we start with our original matrix, X, omega, with the missing entries. And so the missing entries are the sort of dark green ones in here. And the first thing I'm going to do is tensorize each one of the columns. So now I'm in a D plus 1 choose 2 dimensional space. And now in this higher dimensional tensorized space, I'm going to perform low rank matrix completion. Now what I need to do is fill in the missing entries in my original matrix here, which is not in the tensorized space. So what I do is I recall that when I did this tensorization, I was taking the Kronecker product of the column with itself. And so what I can do is I can take this column that I've completed, which should have this nice tensor structure, and I can reshape it into a square, and note that the first singular vector of this square is going to be that low original D-dimensional vector that I'm interested in. And so I can compute that SVD and use it to fill in my missing entry in my matrix. So this is a one-shot method. It is possible to iterate it. So once I've used this approach to infer missing entries, then I can plug those inferred missing entries into the missing entries up here and then repeat the whole process over and over again. And I'll post the slides later, and so I've got a more algorithmic description of it. But what I really want to focus on is, can this work, and how well can this work? Yeah,
One
Andre.
of this question is that if you try to do it this with the Netflix data set, you get lots of rows, right?
Yeah, that's right. So I don't know if you heard, Andrea was saying, look, in Netflix, for instance, D is pretty huge, and so
20,000.
20,000, so going to essentially a D squared dimensional space is pretty problematic, which is correct. So I'm going to talk more about algorithmic aspects later on. There are some kernelized approaches that we could use. They have their own sets of disadvantages, and so we're still sort of working out what's the most efficient way to leverage these ideas. But before we delve too much into algorithms, I just want to think about whether this is at all reasonable. Like, is this going to, even if we had the resources to do this, are we going to get something that's correct? So I said that we're working with these tensorized representations. So X omega is our original matrix, and again, we've got M observed entries per column. And so when we do this tensorization, then all of a sudden we're going to have M plus 1 choose 2 observed entries per column. So if in my original vector I don't observe x3, then in my tensorized space I'm not going to observe x1, x3, x2, x3, or x3 cubed. And so it's a reasonable question to ask, like, once I do this tensorization, am I going to have so much missing data in this tensorized space that I'm not going to be able to really perform low rank matrix completion? So let's think about that question in the context of a union of subspaces. So imagine I've got k subspaces, each of rank r. Then the rank of my original matrix is k times r. The rank of my tensorized matrix is k times r plus 1 choose 2. Now in general, if I want to do low rank matrix completion for a matrix that has rank capital R, then I'm going to need at least capital R observations per column, just by a simple degree of freedom kind of argument. So let's see if that sort of pans out, or what that suggests. So in the original space, without doing any tensorization, the rank of our matrix X is k times R. So M, the number of observed entries per column, has to be at least k times R. In this tensorized space, the rank is k times r plus 1 choose 2. The number of observed entries per column is m plus 1 choose 2, and so this has to be greater than our rank, or neglecting some constants, it means that m needs to be bigger than the square root of k times r. So what this is suggesting is that by moving into this tensorized space, even though on one hand you might think that we are kind of exploding the amount of missing data that we have, in fact we can get by with fewer observations per column by exploiting the additional structure that we have in this tensorized space. Okay, now like I said, this is just a degrees of freedom kind of argument, so it's comforting that it checks out, but it's not the full story. So in particular, when we work in this tensorized space, we have to think about, well, what are the locations of the observed entries? In a lot of the low rank matrix completion literature, you might assume, for instance, that the locations of the observed entries are distributed uniformly at random. Since we are getting this matrix that we're going to complete by performing this tensorization, they're definitely not uniformly distributed at random. So imagine that I'm in 3 dimensions and I observe 2 entries per column. So there are 3 possibilities. I can observe the first and second, the first and third, or the second and third. And so if I tensorize any of these 3 columns, then these are the sampling patterns that I can possibly observe in my tensorized matrix. So there are all kinds of sampling patterns that a lot of the low-rank matrix completion literature might assume are available to me that are absolutely not available when I'm working with this tensorization mechanism. There's no way I could have a column in the tensorized space that only contains x1 squared, x2 squared, x3 squared, because it's not possible to get that via the tensorization. And so the question is, because I'm very limited in terms of what kinds of sampling patterns I can have in this tensorized space, is that going to affect my ability to perform low-rank matrix completion in that tensorized space? So to get at that, what we're going to do is take a little detour into some previous work on subspace identification. So we're going to ignore all the tensorization stuff for a moment and just think about sampling patterns and how sampling patterns can be used to identify subspaces. And this is based on some prior work from a couple of years ago from my co-authors Daniel Pimentel-Alarcon and Rob Nowak and our colleague Nigel Boston. And in general, if the columns of X of our matrix lie in an R-dimensional general position subspace, then we're going to need R plus 1 samples per column, and that's information theoretically necessary and sufficient. And let me give you a little bit of intuition about what's going on here. I'm not making any distributional assumptions about where these samples are located. But imagine that I had a one-dimensional subspace that my columns would lie upon, and I observe these 2 columns in my matrix. So with the first column, there are many possible values for that missing entry, and they correspond to the blue dots that I've written down here. And the corresponding one-dimensional subspace could be any one of these little blue lines that I've just drawn here. And similarly, if I look at the red column, when the missing value in the first coordinate could be any one of these red dots, and the subspace that this column lies on could be any one of these red lines. And so together, these 2 columns tell me that there's only one subspace that's one-dimensional and consistent with these 2 columns, and I can identify that subspace, and it tells me exactly what the missing entries should be. Okay, so let's look at a slightly more complicated example to build up our intuition here. So imagine that we've got a matrix, and the columns lie in a 2-dimensional subspace of R4, and that subspace is the span of these 2 vectors, a constant vector and a alternating 1 minus 1 vector. And then imagine that this is our set of observations. So from a kind of algebraic or geometric perspective, we could first look at this submatrix, and we could say from this submatrix we have enough information to estimate a subspace or a basis for the subspace in the first 3 coordinates. So we don't know anything about the 4th coordinate, but at least in the first 3 coordinates we can get a basis for this subspace. And if we look at the last 2 columns, this gives us a basis for the subspace in coordinates 1, 2, and 4. And so now what we need to do to learn an overall basis for our subspace is we need to kind of stitch these 2 together. And here at the top, we've got 2 rows that are in both of the bases. And so the overlap here allows us to align or rotate those two different bases in order to find a full basis for the subspace R4. So again, this is based on an algebraic argument with much more formally stated proofs in this prior work that allows us to talk about what needs to be true about different sampling patterns to ensure we can identify subspaces without assuming things like the locations of the observed entries are distributed uniformly at random. And so what we'd like to do is now leverage this in the context of these tensorized sampling patterns. Okay, so this is the picture that I showed before. If we had three-dimensional samples and we're only observing 2 samples per column, then these are the 3 different sampling patterns that are possible. And in the tensorized space, these are the 3 different sampling patterns that are possible. Nothing else is possible. And to keep things a little bit cleaner in the following slides, I'm going to write this in terms of zeros and ones. So it's a slight shift in notation. So what I mean by this matrix here is that these columns correspond to all the different sampling patterns available to me. So when I actually observe my matrix X omega, I might have multiple columns where I only observe the first and second entry, and multiple columns where I only observe the first and third entry, etc. So this is just the possible sampling patterns that I can have in 3 dimensions if I observe 2 samples per column. And similarly, these are the sampling patterns available to me after I do this tensorization step. And so again, the question is, when I have these strong restrictions on the space of different sampling patterns, is that going to hurt me? Am I still going to be able to perform low-rank matrix completion in this tensorized space? And the answer is that it can be a problem. So here's an example where we have a problem. So imagine that the columns of X lie in a union of 2 one-dimensional subspaces. Sorry, I have a typo here. The union of 3 one-dimensional subspaces in R3. So the rank of X is equal, in this case, to the rank of the tensorized X, which is equal to 3. And then imagine that we have 2 entries per column that are observed. So clearly, this is insufficient for us to be able to do matrix completion of any type in our original space. If we've got a rank 3 matrix, we're only observing 2 entries per column, there's nothing we can do. If we do this tensorization, then it's maybe not quite as obvious on the surface, but we can make a similar argument to what I was making on the previous slide. We can say, well, let's look at these last 3 entries of this last column. From here, we can identify a basis for the subspace in the last 3 coordinates, but this is because there's not very much overlap with the sampling patterns in the other 2 sampling patterns. There's no way we could ever align that basis with the bases that we could learn based on sampling pattern 1 or sampling pattern 2. So this is a case where even though we've got sort of where we cannot perform or identify the subspace. But this is not always the case. So here's a maybe nicer example. So again, we're going to assume that the columns of X lie in a union of subspaces. Now we're going to work in a 5-dimensional space, and we've got the union of 5 different subspaces. So the rank of X and the rank of the tensorized X, those are both 5. And we're going to observe 4 entries per column. So again, clearly in our original observation space, there's just not enough information to ever do low-rank matrix completion. If we look at the tensorized space, suddenly things look a little bit nicer. So the first sampling, or the last sampling pattern here, tells us that if we have lots of columns that all are observed on these entries, then we can use those columns to estimate a basis for our 5-dimensional subspace in those last 10 coordinates. In addition, there is an overlap in this second to last column of 6 different coordinates, in addition to getting information about these 4 different coordinates here. And so we can use information about this second to last column to form a basis for the first, third, fourth, and fifth coordinates, and align it with the basis that we learned for the last column. And so we are avoiding or sidestepping the problem we saw in the previous case. So yes, in this case, we can identify the basis for the subspace in this 15-dimensional space because of the overlap among the sampling patterns. Okay, so this is a nice example of a setting where we have an algebraic structure underlying our data. If we were to try to do low-rank matrix completion, it would be impossible. And yet by moving into this higher dimensional tensorized space, it is possible to perform low-rank matrix completion and therefore infer the missing entries in our original space. Okay, so we formalized this with less hand-wavy arguments in the paper and said, imagine that this sampling set omega, or a set of sampling patterns omega, contains all D choose M different sampling patterns that are possible in this tensorized space. Then mness, or m necessary, is going to be the smallest integer so that mness plus 1 choose 2 is greater than the rank of our tensorized matrix. So let's look at the bottom line first. As long as the number of samples per column is greater than mness plus 2, then the subspace can be uniquely determined. So we can actually perform low-rank matrix completion, or we can actually, determine the subspace. If m is less than this necessary threshold, then we cannot determine the underlying subspace, and then in between there are a couple of cases where it cannot be uniquely determined. Okay, so we've got these nice sharp bounds on what is necessary in order to be able to identify the subspace in this tensorized space. And what we see is that the bounds showing up in this theory are reflected by phase transition plots that we computed in some simulations. So here we randomly generated data from a union of subspaces. So we were working in a 15-dimensional space. Each of the subspaces in the union was 2-dimensional. And we ranged the subspaces from 1 to 20. And that's what you're seeing on the horizontal axis in each one of these plots. And we also looked at a range of sampling densities. So we looked at m over d, or the fraction of observed entries per column. And what I'm showing here is, well, white is good, so I'm looking at the fraction of times that we were able to recover, I think 99% of the missing entries. And what we're seeing is that with low-rank matrix completion, just like our theory predicted, we have this phase transition right at this red line, which corresponds to the situation where m scales like k times r, the number of subspaces times the dimension of each subspace. And in contrast, if we were to do this iterative low algebraic dimension matrix completion, we get a phase transition that seems decently aligned with the theoretical bound of the square root of k times r, which is a non-trivial advantage. And we even compared this with some other approaches that you might use that are designed explicitly for unions of subspaces, where you have to do this initial clustering step that I said was problematic for most of those algorithms. So we looked at an expectation maximization algorithm. We also looked at sparse subspace clustering with entry-wise zero filling, which was shown by René Vidal's group in 2015 to empirically be one of the best approaches out there for dealing with unions of subspaces. And so what we're seeing is that by working in this tensorized space, we can see some non-trivial empirical gains. Okay, so as Andrea mentioned, computationally this can be problematic because we are having to go from working in a d-dimensional space to effectively a d-squared dimensional space. And so in the interest of time, I'm not going to walk through all of the details of this, but we did develop a tensorized version, a kernelized version of the algorithm, where we use a polynomial kernel that corresponds to the polynomial order of our tensorization step, and fold that into an iterative reweighted least squares algorithm. And what we see empirically when we look at these phase transition plots is that when we use this low algebraic dimension matrix completion, where we explicitly tensorize all the columns, then the computation is quadratic in that ambient dimension. And if we work with our kernel-based approaches, which is called variety matrix completion here, then we have a computation that's quadratic in the number of columns. And you can see that empirically there are some trade-offs depending on how you measure success, whether you're looking for 100% success or you're looking for 95% success. Sometimes one method works better and sometimes another method works better. And so one of the things that we're actively looking at is whether there are some first of all, some clarity on what works better when and why, and also whether there are some in-between algorithms that are quadratic in neither the ambient dimension nor in the number of columns. But we have tested these kinds of approaches on real data as well. So one benchmark data set that we see often used in the union of subspaces literature is on motion segmentation from a data set developed by Johns Hopkins University, where they're trying to segment different trajectories of different objects in a video sequence. And so we looked at the performance of our method for imputing missing values, followed by subspace clustering, and these are the lines in red, and we're showing the clustering error as a function of how much data is missing. And we compared that with doing subspace clustering just with zero filling instead of doing anything fancy to fill in the missing entries, or using low rank matrix completion followed by subspace clustering. And what we can see is that in settings where the underlying matrix really is low rank, that low rank matrix completion plus subspace clustering does as well as our methods. But as we move into regimes where there is less and less low rank structure overall, and where you really have to leverage the union of subspaces, there's a pretty significant advantage to using these algebraic variety-based techniques. So as I said, this is ongoing work. There are still open questions regarding the best ways to implement these ideas effectively. As I said, we've developed some naive kernel methods, but there are potentially some methods for improving the speed of those kernels. In addition, one of the things that I have not addressed in the theory that I've described so far is how the error scales as a function of the number of columns in my matrix. So in the theory that I described so far, I assumed I just had lots and lots of columns for every possible sampling pattern, and we're working to refine that now. So thank you very much. There are two papers on this, one that was in ICML last year and another that was at the Allerton conference last year. And I'd be happy to answer any questions.
When the polynomials used to define this algebraic variety, if that polynomial is higher order, then I guess sometimes you will need like a third order tensors or higher order tensors. So now you only talk about second order.
Right, so the question is about higher order tensors or higher order polynomials. So first of all, you could imagine taking the algorithm that I described in some detail and looking at higher order tensors, but then this explosion in the dimension becomes even worse. And so it's not something that I think is practical. The kernelized version of our algorithm, it becomes trivial to work with higher degree polynomials, at least algorithmically. The effect of noise, however, as you go to higher order polynomials is unclear. So here we've been studying a noiseless setting. If you start working with higher order tensors, then noise could become problematic. Finally, I just wanted to mention that what we're really exploiting here is the fact that if we do some tensorization, we have some low rank structure. So even if you've got an algebraic variety that's defined by fifth order polynomials, it's still possible that you can do this quadratic tensorization and still end up in a rank deficient state where these methods could provide you some improvement. So going to a higher order polynomial could potentially yield even more improvement, but what we're seeing is that even just sticking with a quadratic tensorization yields some substantial gains.
Yeah, but I guess in general, which order tensor needs to be used depends on the subspace, right? The underlying subspace.
So I'm saying I disagree with that. So I'm saying that perhaps you could go up to the higher order tensors and see some gains, but even with a quadratic tensor, when you have a higher order polynomial variety, even the quadratic tensor buys you something. I mean, think about the union of subspaces setting, right? The union of subspaces can be low rank even without any tensorization. If I do quadratic tensorization, then I have I've got some low rank structure in that space. If I go to a cubic tensorization, then there's some low rank structure in that space. And so then you start having to really play with the trade-off between, well, what is the rank in the higher order tensorized space, and what is the structure of the missing data in that space. But it's not the case that I have to go all the way up to the degree of my variety. It's more of a smooth transition.
Thank you for your nice talk. I have an intuitive doubt. Couldn't be a single observed dataset compatible with many subspace patterns? That is, there any uniqueness results or anything like probability scenarios for different possible compatible subspace patterns?
So I'm not sure I completely understood your question. Are you saying, are there real data sets where we would have multiple columns that all have the same sampling pattern?
Exactly.
Right. So it's hard to say. I believe that the results that we've shown here are conservative in terms of assuming that we have as many copies as we want of each possible sampling pattern. And certainly in our experiments with real data, that's not always the case, and yet we're still seeing some gains. And so I think that our theoretical results are more conservative and maybe weaker than what, or based on stronger assumptions than are really needed in practice. But we haven't refined that yet. Yeah.
Thank you.
Thank you.